Good day. This is the video presentation for the discussion class for the topic of line integrals of vector fields and work. In the lecture class video, you learned the definition of line integrals of vector fields. And this definition, if I may recall, is motivated by the problem of computing the work done by a force field F acting on a particle moving along a smooth curve C parametrized by a vector-valued function r of t, where t runs over the interval AB. So for this video, we have two objectives. First, we will be evaluating line integrals of a vector field F over a curve C parametrized by a parametric curve r of t, where t is from A to B. And we will also be computing the amount of work done by a force field F in moving a particle along a parametric curve r, where the parameter t runs from A to B. Let's start. So we have 6 problems, and the first of the 6 is the following problem here. So let us find the line integral of f over c, where the function f is the vector-valued function whose first coordinate is x squared and the second coordinate is negative of xy. And the curve c is the curve parametrized by r of t given by cosine t sine t, where t is from 0 to pi. Now for our solution, let us recall that the line integral of f over c is given by the definite integral of f evaluated at r of t dotted with r prime of t dt from A to B, where the curve C is parametrized by r of t and t runs from A to B. Now, our function f is x squared negative xy, and so if we plug in cosine t to x and sine t to y, we obtain our function f evaluated at r of t, which is cosine squared of t negative cosine t sine t. On the other hand, the derivative of r of t is given by the vector whose coordinates are the derivative of cosine t, which is negative sine t, and the derivative of sine t, which is cosine of t. So given these two vectors, f evaluated at r of t and r prime of t, we compute the dot product. Okay. Now the dot product is the dot product between the vectors cosine squared t, negative cosine t sine t, and negative sine t cosine t. And so we get cosine squared t times negative sine of t, so we get negative sine t cosine squared of t, and negative cosine t sine t times cosine t. So that will be negative cosine squared t sine of t. Now simplifying, we get negative 2 cosine squared t sine of t. So to compute the line integral of f over c, we need to compute for the integral of negative 2 cosine squared of t sine t from t equals 0 to t equals pi. Okay. Now to solve this definite integral of negative 2 cosine squared t sine t from 0 to pi, we use the substitution method and we let u to be cosine of t. Now, given this substitution, observe that d of u is equal to negative sine of t. And the upper and lower limits of integration will be replaced with cosine of 0, which is equal to 1 as the lower limit, and cosine of pi, which is equal to negative 1 as the upper limit. And therefore, the line integral of f over c is equal to the integral of 2u squared du from 1 to negative 1. And now evaluating this integral, we obtain 2/3 of u cubed evaluated from u equals 1 to u equals negative 1. And so we obtain 2/3 of negative 1 minus 2/3 of 1, which simplifies into negative 4 over 3. So the line integral of f over c is equal to negative 4 over 3. Okay, so let's move on to the next example. For the second problem, we again want to compute for the line integral of f over c, where f is the vector function x squared plus 5y squared 3x squared y, and the curve c is the portion of the parabola y equals x squared from the point -1, 1 to the point 1, 1. Okay, so first we need to parameterize the curve y equals x squared. So a possible parameterization of this parabola is given by r of t, which is equal to the vector function t squared. So here observe that we just represent x by t, and so correspondingly y will be t squared. So this is a possible parameterization. Now, since in the problem x runs from -1 to 1, so here t will also run from -1 to 1. Note that any other parameterization of the given curve can be used to compute for the line integral. Okay, so now let us use this parameterization r of t to compute for this line integral. Okay, so what is f evaluated at r of t? So we plug in t to x and t squared to y. And so f evaluated at r of t will be t squared plus 5t to the 4th power. So that will be the first coordinate. And the second coordinate will be 3t squared times t squared, which simplifies into 3t to the 4th. So this is f evaluated at r of t. Now, the derivative of r prime of t is given by 1, 2t. So we now need to get the dot product of f with r prime, and we get the dot product of t squared plus 5t to the 4th, 3t to the 4th, dotted with the vector 1, 2t. And so we get t squared plus 5t to the 4th times 1, which is t squared plus 5 to the t to the 4th, plus 3t to the 4th times 2t, which is 6t to the 5. Okay, we now need to integrate the dot product between f evaluated at r of t and r prime of t from -1 to 1. Now the integral of t squared is t cubed over 3, and the integral of 5t to the 4th is t to the 5, And the integral of 6t to the 5 is t to the 6. And so all we need to do is to evaluate this sum from -1 to 1. So plugging in 1 to this sum, we get 7/3. And plugging in -1 to t, we get -1/3. So this integral here is equal to 7/3 minus -1/3. And so the answer is 8/3. So the required line integral of f over the parabola c from the point -1 to 1, or rather, from the point -1, 1 to 1, 1 is 8/3. Let us now move on to the third problem. So for the third problem, we want the line integral of the vector f over c, where the function f is the vector valued function whose first coordinate is -y and the second coordinate is x. And the curve c is the circle of radius 2 centered at the point 1, 0, traced counterclockwise once, starting from the point 3, 0. So let us start solving this problem by first parametrizing the curve C. So the curve C is a circle, so we can write C in the center radius form. So the circle in the center radius form is given by x minus 1 squared plus y squared equals 2 squared. Now we can divide this equation by 4, and so the equation for the circle can be rewritten as x minus 1 over 2 raised to the second power plus y over 2 raised to the second power equals 1. So we can let this expression x minus 1 over 2 as cosine t and the expression y over 2 as sine t. And so we have x minus 1 over 2 equals cosine of t, and y over 2 is equal to sine of t. Observe that when we square cosine t and square sine of t and add the two results, we will get 1. Now, with this representation, solving for x and y, we obtain that x is equal to 2 cosine of t plus 1 and y is equal to 2 sine of t. So the curve C can be parameterized by r of t equal to 2 cosine of t plus 1, 2 sine of t, where t runs from 0 to 2 pi. So all we need to do now is to evaluate the function f at the function at the function r of t, and compute for the derivative of this function r. So plugging in this to x and plugging in 2 sine of t to y, we will get f evaluated at r is equal to negative 2 sine of t, comma, 2 cosine of t plus 1. And the derivative of r is the derivative of 2 cosine t plus 1, which is negative 2 sine of t plus 0. And for the second coordinate, the derivative of 2 sine of t is 2 cosine of t. So now we need to get the dot product between f evaluated at r of t and r prime of t. Now the dot product is the sum of negative 2 sine t times 2 sine t, that will be 4 sine squared t, and 2 cosine t plus 1 times 2 cosine of t. Now what is that product? So we have 2 times 2 is 4. Cosine of t times cosine of t is cosine squared of t plus 2 cosine of t times 1. So we have this sum as our dot product, which simplifies into 4 plus 2 cosine of t. So now we need to get the definite integral of 4 plus 2 cosine of t from t equals 0 to t equals 2 pi. And so we will have that the integral of f evaluated at r dot r prime over the curve C is equal to the definite integral of 4 plus 2 cosine t dt from 0 to 2 pi. The integral of 4 is 4t. The integral of 2 cosine t is 2 sine t. So we need to evaluate 4t plus 2 sine t from t equals 0 to t equals 2 pi. Note that when you plug in 0 to t, you will get 0. And so we just need to evaluate t at 2 pi. So we get 4 times 2 pi is 8 pi. And we have 2 sine of 2 pi, which is equal to 0. So the line integral is equal to 8 pi.